Okay, guys, so we're going to catch the last few pieces of Chapter 5 with the global ocean circulation that I inadvertently left out of the last lecture. Sorry about that, along with the internal planetary processes. All right, so make sure you guys are, again, following up these lectures with making the reading, making time for the reading out of the chapter. All right, so global ocean circulation. So we are talking about currents in this case, right? And we'll do a quick differentiation. We have what are called surface and deep ocean currents, right? And so surface currents, as the name implies, we're talking about the currents that we get at the surface of the ocean. And deep ocean currents involve a mixing vertically of the surface with the deep ocean waters. And we'll talk about different processes that cause those over here in a little bit. But looking at our surface currents, which is what we see in this diagram right here, we'll notice that we get these circular ocean patterns, right? Or circular current patterns, right? So here and here, those circular patterns are called gyres, G-Y-R-E-S, right? So gyres are our circular surface ocean currents, and those are driven primarily by our prevailing winds. Right, so again, if you think about it, our trade winds blow to the east, so we can see that portion. Our westerlies blow from the west, and that creates these patterns, right? So notice that those don't spin the same direction as our hurricanes, interestingly. All right. Anyways, so our circular ocean currents are caused by the prevailing wind directions, and those circular ocean currents are called gyres. All right. Now, another important cause of the patterns we get in our ocean is the position of land masses. So it is important, and especially actually in our next chapter as we talk about a little bit more with the carbon cycle. I know you guys are thinking, how could there be more? But the position of land masses is important for our ocean circulation because they do kind of block the direction of our ocean currents. All right. Now, moving to our deep ocean currents. Now, these are density driven. All right, so the density of our ocean water is determined essentially by two factors. One of them is temperature. So warmer water is less dense than cold water, but also by salt content. So our saltier water, the more salt we have in our water, generally the higher density we have. Okay, so we have what's called the ocean conveyor belt sometimes. Whoops, sorry about that. Ocean conveyor belt, right? Refers to this ongoing and slow vertical mixing of water. So this blue section here refers to the direction of flow of water in our deep ocean. And that water is salty and cold, right? It is denser. All right. Now, at certain locations, right, we get either an upwelling or a sinking of our water. Okay. And that is primarily driven again by density. As we approach the poles, for example, we tend to get colder, right? And so sinking water at the poles, particularly over here by Greenland in the North Atlantic. All right. And then we tend to get rising water in the Pacific. Okay, but again, I mean, we're talking, if you were to trace like a single water molecule through this whole thing, we'd be looking at thousands of years for it to make that entire trip. So it's a slow process. But again, so our surface currents, those circular currents are called gyres. Those are driven by our prevailing winds. Our deep ocean and vertical mixing of the ocean is driven by density differences, and it's a much slower process over time. All right. So we have what are called ENSO cycles, and you guys have heard of most likely El Nino and La Nina cycles, particularly how they affect weather patterns. Well, an El Nino, which again we will talk about in more detail or in some detail in the next chapter, but it's a periodic large-scale warming of surface waters on the tropical or equatorial eastern Pacific Ocean. All right, so I'm actually going to, and this is important because it does alter both ocean and atmospheric circulation patterns. So we should be familiar with the idea that the temperature of our oceans and the position of our oceans affect our climate therefore atmospheric circulation. All right. So in normal conditions, right, the trade winds that blow from the east toward the west, they tend to blow our warmest water into the western Pacific. And I'll show you guys a diagram of this in just a second. Right. During El Nino conditions, right, those trade winds slow down a little bit. And so some of that, so again, normally we're blowing our warmer water toward the western Pacific from the east, right? What happens is when those trade winds weaken, it allows a sort of a backflow of that warm water back toward South America. All right. And what that does is, it's a periodic warming of the surface waters in the eastern Pacific, which would be towards South America. So if we look here during El Nino, so here's South America, right? So normally we're blowing our warmest water that direction. When those trade winds weaken, right, we actually get a backflow of that warmer water, and so we get warmer than average waters on the equatorial Pacific, especially near South America. Now, the result of that warmer water varies from location to location. Some locations really aren't impacted at all, at least not very much. Some locations end up warmer, some end up cooler, some end up wetter, some end up drier, some end up some sort of combination of the two. So as you can see from this part right here, up here in Washington, we usually just end up a little bit warmer, and there's not an appreciable impact on our precipitation patterns. Although here in Walla we're kind of on the fringe of that, so we don't tend to see much of an impact. Now, notice that California usually ends up a little bit wetter, along with Southern Oregon and so on. But not necessarily warmer. The temperatures stay the same. So often our big snowpack years down the Sierra Nevadas are accompanied by some sort of El Nino. Okay? Now, an El Nino year does not mean we're going to be warmer that winter, for example. It does not mean we're going to get more precipitation. It just kind of increases the likelihood of warmer weather or precipitation patterns. All right. So, moving on to our internal planetary processes. All right. So, with internal planetary processes, the College Board wants you guys to have some familiarity with plate tectonics and the processes that cause our lithospheric plates to kind of shuffle around at a really slow pace. All right. Particularly with how they tie in with things like volcanic activity and earthquakes, etc. All right. So, first of all, the layers of the Earth. If you are taking a basic Earth science to kind of split the layers of the Earth into like the crust, mantle, inner and outer core, in the world of geology, we actually use slightly different layers. We refer to what's called the lithosphere, which is our outermost rigid rock layer, and it's actually composed of the crust and upper mantle. All right. And so it's the portion of the Earth that it's solid and rigid. Rigid meaning it doesn't really bend or anything like that. Now, the asthenosphere is composed of our lower mantle, and it's composed of hot and soft rock. Okay? So the way to think about it is it's really, really hot, yes, but it's not so hot that the rock is completely molten. It's a property in geology kind of referred to as plastic. And in that case, that means it's not liquid, but it's hot enough that it becomes sort of pliable, almost like really hot glass. It's not quite melted, but hot enough to where you could actually start to bend that glass. That's sort of the consistency of the lower mantle or the asthenosphere. All right. Then moving down, we have our outer core, which is actually mostly metal, iron and nickel, and it is hot enough to actually melt that metal. And then the inner core, because of pressure, just as hot and made of the same composition, but it is solid, right? And you might be wondering how they know these things. There's a whole field called geophysics, and it has to do with the properties of waves and how they travel through various materials, which types of waves can travel through liquids versus not, and so on. So there's lots of evidence to support this, but no one's ever dug down deep enough to actually to see these things. All right. And so plate tectonics is the study of the process by which lithospheric plates, so that's that rigid part, our outer layer of the crust and upper mantle, move kind of on top of this plasticky asthenosphere, which again, when I say plasticky, that means pliable, right? Like really hot glass, not made of plastic, of course. All right. And of particular importance to us, of course, is what we call plate boundaries, which is where two lithospheric plates meet. And that's the common site of our earthquakes and volcanoes, which is really what we're getting to here. All right, so if you were to look at a map of the world and identify where our plate boundaries exist, you see that there is plate boundaries going down the interior of our oceans, right? Those are what we refer to as oceanic ridges, right? And there's lots of plate boundaries along lots of our continents as well. And we'll talk about the significance of the divergent versus convergent versus transform here shortly. All right. So moving forward, a divergent plate boundary, right? So this can, like I said, much in this chapter I could spend a whole semester teaching. So we're going to go really basic here. So a divergent boundary is typically going to be our mid-ocean ridges, although not always, but often our mid-ocean ridges. And divergent means spreading away from each other. So at this type of boundary, we have rising magma, right? That kind of causes an upwelling, and then that causes our plates to slowly spread apart. So we have new crust forming at the boundary, and then as you work your way away from that boundary, that crust gets older. Okay, so new crust at the boundary, older as you move away. Divergent means moving away from each other. Okay, so most of our mid-ocean ridges are divergent boundaries. So these blue. Okay, now a convergent refers to the convergence of two plates. All right, and at a convergent boundary, that's where the plate motions are toward each other. So they're actually colliding in a sense. Although what you guys have to understand is the rate at which these plates move is extremely slow. In the fastest places, they move about the rate at which your fingernails grow. All right, so we're talking really, really slow movements over extremely long periods of time. Okay, so as these two plates converge, right, we get some common features are volcanic activity, right? And depending on what type of plates are meeting, if an oceanic plate is involved, we get what's called subduction, right? So let's say we have a continental plate and an oceanic plate. The oceanic plate is more dense, all right? And as that oceanic plate converges with the continental plate, because the oceanic plate is more dense, it is forced downward. And that's what we call a subduction zone. Very, very key point, right? So a subduction zone occurs, right, when an oceanic plate converges with another plate, right? And one of those plates, the denser one, is forced downward into the asthenosphere. That's subduction. And as that plate is forced downward, some of that crustal material is exposed to the intense heat of the deeper earth, right? That causes molten rock to rise to the surface, right? And that is how we get volcanic chains to form. So if we go back here, right? So notice we have subduction zones where we have an oceanic plate and a continental plate occurring along the west coast of the United States, right? So right here through Washington, we have Mount Hood, Mount St. Helens, Mount Baker, Mount Rainier are all volcanoes. Along the coast of Alaska and the Aleutian Islands are volcanic. That same subduction zone extends over on this side, right? Down the coast of Japan, our South Pacific Islands, right? Those are all volcanic. So again, where we have convergence of an oceanic plate with another plate, we often get subduction. Subduction, right, exposes crust material to the intensity of the internal earth, which can melt it. That molten material can rise to the surface to create volcanoes. All right. We often get oceanic trenches. So the deepest parts of the ocean, right, are associated with subduction zones as well. All right. And the last type of boundary we're going to talk about are what's called the transform plate boundary. And that's where we're not converging or diverging, but they're kind of moving parallel to one another, often in opposite directions. All right. And so the most common referred to place is the San Andreas. Right. And that's in California. So if we go back here again, right here, right, in Southern California, we have a transform boundary where the plates are sliding parallel to one another. And transform boundaries don't tend to form volcanic activity. All right, but they are often associated with earthquakes. Okay, which is why California is so famous for its frequent earthquakes. Okay, so again, 3 types of plate boundaries: divergent, convergent, and transform. Divergent occur along our mid-ocean ridges mostly. There's also a divergent plate going through Africa. Okay, convergent is where we have 2 plates colliding. If an oceanic plate is involved, we often get subduction and volcanic arcs. If it's 2 continental plates, we get mountains but no volcanoes. All right, and then of course transform boundaries are where they're moving parallel to one another. We don't get volcanic activity, but we do get frequent earthquakes. And keeping in mind that earthquakes can happen pretty much anywhere. They're not entirely isolated to our plate boundaries. But earthquakes happen at transform, divergent, and convergent boundaries. Okay, so an earthquake is caused by the sudden release of accumulated energy. So again, we're talking about really, really slow processes. So if I have a convergent boundary, for example, right, that creates some tension, right? And this is a really, really slow process. And so we don't tend to just move at a snail's pace. The tension tends to build up over time, right? And then eventually there's a sudden slip, right, which releases a lot of energy. So it's a sudden release of accumulated energy along fault lines, right? And as that energy is released, so let's say we have the focus of an earthquake, that energy is released out in all directions from that focus in wave patterns. All right, so the focus is the actual site of an earthquake, typically well below the surface. The epicenter is located at the Earth's surface directly above the focus. So let's say I have a fault line here, right? So here's my surface. This is my fault line. Let's say I get the earthquake actually occurs. This is the focus, deep beneath the surface. The epicenter would be the location directly above that focus at the surface. All right, so oftentimes in the news, if you hear about an earthquake, they talk about the epicenter. They're talking about the surface location directly above the focus of the earthquake. All right, and we measure the intensity of earthquakes with what's called the Richter scale. All right, the higher the magnitude and on the Richter scale, the more damaging that earthquake is, and it's actually an exponential scale, but I don't have time to get into that right now. All right, now if an earthquake or a volcano erupts underwater, again, we're talking about the sudden release of energy, right? And so in the case of a tsunami, right, we're talking about an undersea wave caused by some sort of underwater earthquake or underwater volcanic eruption, right? That causes a sudden displacement of water, right? So the way to think of this, let's say here's my water, right? So deep underwater, right? There's some sort of earthquake that causes a sudden movement of that water. Okay. Now, what happens as a result of that is you kind of get this most of a tsunami as it travels through the ocean at several hundred miles per hour, right? Travels mostly underwater, and so it can travel through the open ocean extremely fast, right? And as that tsunami travels through open water, it's not really noticeable, right? But when it starts to hit, let's say, our continental shelf near the surface, what happens is this builds up, slows down and builds up, and what you get is this giant wall of water that can reach as much as 60 meters in height. So remember we talked about storm surge in class, right? A tsunami would be like a storm surge on steroids, although it wouldn't last for the duration of a hurricane. It's just a giant bulge of water. It doesn't come in really as just one like crashing waves. It's just a big increase in sea level, but very sudden, right? Now, it does not travel at 450 miles per hour. When it reaches the surface, it slows down, but it carries that water, and then eventually, I mean, it can just wipe out anything in its path. If you get a chance, just type in on YouTube Japan tsunami, and you can watch essentially what that giant wall of water does. It's a ton of energy, just complete devastation of everything in its path. And like I said, they can go up as tall as 60 meters. There's some evidence of tsunamis that have been that high. The one in Japan was not nearly that big, but you can still kind of see the vast amount of damage. But again, tsunamis caused by sudden displacement of water, right, due to some sort of undersea volcanic eruption, landslide, or earthquake. All right. Let me see. So move forward here. Oh, and one more kind of just term to bring up is what's called hotspot volcanism. So Hawaii and Yellowstone, for example, right? They are not associated with plate boundaries. They're actually on the interior of the plate. So sometimes we get volcanoes where there is no plate boundary. Those are called hotspots, and our examples would be Hawaii and Yellowstone. Okay? So hotspot is a location on the interior of a plate where there's ongoing uprising of magma. So Hawaii, Yellowstone are classic examples of that. All right. So 22 minutes, and that's it. See you guys later.